For our next example, we're going to continue using counter-controlled iteration with a for iteration statement. And this time we're going to use the for to help us calculate compound interest. Now, before we look at the actual example, let's take a look at a problem statement. So a person invests $1,000 in a savings account yielding 5% interest, and assuming that all of that interest is left on deposit, we would like to calculate and print the amount of money in the account at the end of each year for 10 years. Now, because we're dealing with monetary amounts, once again, we're going to use the decimal data type for the purpose of precise monetary calculations. Now we're going to use the following formula to perform these calculations, where A is going to represent the amount on deposit at the end of a given year, and we'll give these actual variable names that are more descriptive when we look at the source code. The letter P represents the principal amount, and we're going to multiply the principal amount by 1 plus the interest rate raised to the number of years for which we would like to determine the amount on deposit at the end of that nth year. Now 1 plus r is going to be 1 plus 0.05 in this particular example, where 0.05 represents 5% interest. So let's go ahead and open up the corresponding project. You can see here that we're in the figure 06_06 folder in the interest project, and we'll open that up. And we have an interest.cs file that defines the class, which contains, once again, for this example, only a main method. Now, within the main method, we begin by declaring the decimal variable principal, and that's going to have the initial value of 1,000, and we could have certainly declared that as 1,000.0 as well. However, if we do declare it as 1,000.0, notice we're now getting an error message because a floating point value of type double cannot be implicitly converted to a decimal value for storing into a decimal variable in memory. An integer value can, and that has to do with the fact that both decimal and integer values can be represented precisely in memory. So you can use 1,000, or you can say 1,000.0 and then place the letter M to indicate that this is a decimal literal value. Now the interest rate in this example once again is 5%, so 0.05 for the interest rate in our calculations. And we're going to display two columns of information in this example, one with the column head year, which will have the numbers from 1 through 10 in it, and then amount on deposit will represent the amount on deposit at the end of each year. Let me go ahead and run the program before we go ahead and look at the rest of the code, and you can see here that we're right aligning the year values from 1 through 10 under year. So we'll show you how we do this formatting here, and you'll also see that we're formatting the monetary amounts as dollars and cents with 2 digits to the right of the decimal point, and also we have a thousands separator being displayed as well. This is the currency formatting that we first introduced to you back in lesson 4, and we'll be revisiting that here as well, and adding to it the ability to right align the value that we're displaying in a column of values. So we'll take a look at that in just a moment. So that's going to display our column heads for the example, and our counter-controlled repetition occurs here in lines 16 through 24. We're going to be iterating over 10 years, so we decided to use a counter called year and initialize it to 1. We're going to keep iterating as long as year is less than or equal to 10, and after we perform the body of the loop each time, we're going to add 1 to the year so that eventually the loop will terminate. Now, the calculation that determines the amount on deposit at the end of a given year is calculated by lines 19 and 20, where we store in the decimal variable amount the result of the expression that multiplies the principal times 1.0 plus the interest rate raised to the year power. So let's break this down into some smaller pieces here. First of all, we have the method call math.pow. The class called math, which is in the system namespace, defines many static methods that represent various mathematical calculations. Now, these methods are declared static because you don't need to create a math object first in order to pass in a value that should be raised to another value by the POW method. So they're defined as static methods of the class, which allows us to call them via the class name rather than having to create a new object first. And in fact, console.writeLine, which we've been using in all of the examples so far, is another example of a static method of a class. We don't have to create a console object in order to write out a line of text to the command line in our examples. We simply call that method via the class name. So math.pow, as it turns out, and then I'll hover over it so you can see this, math.pow takes two double arguments and returns a double. There is not a version of math.pow for decimal calculations. So what we're doing here is we're taking the value 1.0 plus the rate, which is always going to be 1.05, and we're raising that via math.pow to the year power. And that's helping us determine the value by which we want to multiply the principal. Now, in order to perform a decimal arithmetic calculation, we cannot multiply principal, which is a decimal, with the result of math.pow, which is a double. Again, C# does not allow doubles and decimals to be implicitly converted to one another. So for that reason, we're taking the return value of math.pow and we are casting it to type decimal so that we can have a decimal value principal times the decimal result of this math.pow calculation. And once we finish that, at the end of the calculation, we have the amount on deposit at the end of the given year. We then go down to line 23 and display two columns of information. Our first string interpolation expression here says to display the value of year, and then the comma 4 indicates that we want that value to be displayed in a field width of 4 character positions. And when you have a positive value for the field width, the item that you're displaying within that field of characters is going to be right aligned within the field. If you want left alignment, you can use a negative number instead to get left alignment. So the year is going to be right aligned in a field of 4 in this case. Following that, in a field of 20, also right aligned, we're going to display the amount, and the :C, just like in earlier examples, says that we want to format that value as currency. And that's the reason that, at least in my locale, when we run this program, we're getting $signs, and we're also getting 2 digits to the right of the decimal point, and we're getting a thousand separator, which is a comma. When you run this on your own computer, depending on your locale, you may get different results displayed in this right-hand column. The numerical values would be the same, at least on the left side of the decimal point. Some locales do not use floating point numbers to represent monetary amounts, and in those cases these might show up as whole numbers here, depending on the locale. But as long as you're in a locale that does have the equivalent of what we call dollars and cents here in the United States, then you should see something similar on your screen.